Alright, welcome to this video, and in this video I'm going to be talking about a decomposition reaction of potassium chlorate into potassium chloride and oxygen. And this is a multiple part question, so I'm going to start with the first question here that's going to ask us how many moles of oxygen are produced when 8 moles of potassium chlorate decompose. So we also have a delta H here in this problem. So basically this delta H is the heat of formation. And when we have a positive delta H, that's basically going to tell us that this is an endothermic reaction. And when I say the word endothermic, what I mean is I have to put energy in to make this happen. So for example, this is decomposing. So for this to decompose, I basically had to add heat to watch it decompose. So that's all that means. This is endothermic. And this is going to come in to play later when we ask about the heat of formation. So the first thing I want to do here is I want to have a line here where I'm going to control this equation, where I'm going to have the number of moles written out across here. I'm going to write this out in a minute. These represent the mole ratios here. So this 2 in the front is the ratio that always has to be true for the potassium chlorate, the 2 for the potassium chloride, and the 3 for the oxygen. This equation is balanced. I have 2 potassiums here, 2 potassiums here. I have 6 oxygens here, 6 oxygens here, 2 chlorides here, 2 chlorides here. So it's balanced. So the first thing that happens is I have 8 moles of potassium chlorate that are decomposing. So basically right here I know that I have 8 moles of this that are decomposing. Now since these are just simple ratios, this is nothing more than a proportion, what I can do is I can very quickly find out the number of moles of each that are formed. What I can do in dealing with these mole ratios is basically to multiply the number of moles times this one divided by this one to tell me the proper ratio, and that's going to give me 8. I can take 8 moles here times 3 is 24 divided by 2, that's 12. All that I'm doing is a basic proportion here, okay? There's a long way to do this with mole ratios, but this is just a pretty quick shortcut right here. The reason I like to do that is because I need to control this equation here by having the number of moles that reacted. So even if it doesn't ask us about the moles of potassium chloride, it's always better just to find it. So from here, I can take these number of moles in here and I can control the equation, okay, and I can go out from here and I can find other things like mass and volume and heat, all of this coming out from these moles here. So how many moles of oxygen are produced? The answer is 12 moles of oxygen are produced. Okay. Now there's a long way to do this. The long way to do this is simply to say I start out with 8 moles of potassium chlorate like this, okay? And then I'm going to deal with my basic mole ratio, okay? So the mole ratio comes from these coefficients, which basically says that 2 moles of potassium chlorate, I'll write it out like this, occurs for every 3 moles of oxygen. Okay. Now it's important to keep in mind that this is what we call the theoretical yield. Okay. So when I go ahead and multiply this out, the moles of potassium chlorate are going to cancel, and I'm going to be left with moles of oxygen right here. Okay. So it comes out to be the same thing, 8 times 3 divided by 2. So I'm going to end up with 12 moles of oxygen. Okay. And I get the same thing that I did here. The reason that this works very quickly doing a proportion is that these are all direct variation. In other words, they're just proportions. They're linear equations that vary directly. They pass through the origin. Okay. So when I'm setting these up again, it's just a proportion. 8 times 2 divided by 2 gives me 8. 8 times 3 divided by 2 gives me 12. Okay. So it's a very quick and direct way to solve this. Alright, for the next question, it's going to take the same equation. It's going to ask us if 30.64 grams of potassium chlorate decompose, how many moles of potassium chloride are formed? So we're going to do a very similar concept that we did the last time, except now we're going to go ahead here and I'm going to write out moles here, but we don't have moles to begin with this time, so we have to go ahead and figure out what's going on in terms of the mass here. Okay, so I'm given 30.64 grams of potassium chlorate, and I want to figure out the moles first. Okay, so I'm going to do a little bit of dimensional analysis here. I'm basically going to take grams of potassium chlorate and I want to go to moles of potassium chlorate. Okay, so the reason I'm writing this out like this first is because when we deal with dimensional analysis, it can get confusing very quickly. So I try to minimize the use of dimensional analysis. Sometimes we have to use it. It's not really using the true formulas, and it's just messing around with units until we get an answer. So I don't like to do it too much. Okay, but sometimes we'll do it. We'll just use it sparingly. what I'm going to do here is I'm going to start out with 30.64 grams of potassium chlorate, okay? And I want to turn it into moles. So before I dealt with this here, I went ahead and I wrote up here what I'm starting with, what I want to finish at. So I'm basically going to be dealing now with the molar mass of potassium chlorate. The molar mass of potassium chlorate is 122.55 grams of potassium chlorate per 1 mole of potassium chlorate. Okay, so that's my basic conversion. That's what I want to get right now out of this question. So I'm going to cancel out the units here. I have the units and I have the molecule. They should always be written together to know what I'm getting. So my final unit is going to be moles of potassium chlorate. So it's important to write all of this out. Don't skip any steps when you do this, because if you skip a step, it's going to give you issues. You're not going to be able to follow what you did, and your teacher might not be able to follow the steps that you took to get here. So we end up with 0.25 moles of potassium chlorate. That's what we're starting with. And the reason I'm doing this off here on the side is because the whole point of controlling a reaction, understanding how it works, is to understand the relationship of the moles. Okay, so I'm going to go ahead and write this underneath here now. Now I have 0.25 moles of potassium chlorate. That is the number of moles of this that I have. Now I can very quickly go through this and figure out the ratios of all of the other compounds that are formed. Okay, so for example, right away I can say, okay, I want to look at potassium chloride. I can say 0.25 times 2 divided by 2, so that just gives me 0.25 right here. If I say 0.25 times 3 divided by 2, I can get the number of moles of oxygen, which is 0.375. Now, even though the question is not asking for that, it's important to understand the whole picture here, because once I have moles, once again, I control the problem. So the way that I'm teaching this is basically to use a little bit of dimensional analysis to get the number of moles, go back to the original equation, write the moles underneath here, and then if we need to go from moles to grams, we can do it from here. But at least we understand the big picture here. Otherwise, when we deal with dimensional analysis, this just goes on and on and on and on and on, and students can get lost very quickly. It's not that it's wrong, it's just that dimensional analysis can be a lazy way to get answers instead of doing it correctly in terms of the correct equation or writing out a table. And this is doing nothing more than organizing information. All I'm doing is organizing the data here. I'm not doing anything mysterious. This is not a different methodology. This is just organizing what we have here. Okay, so we know right away, okay, I have 0.25 moles of KCl. So that's basically it. That answered that question to get the number of moles of potassium chloride from that. Okay. Also important, pay attention to what you have here. We have a solid, and we also have a gas here. So if we have a gas like this, then we could be asking questions about volume later on. And I have a solid here, and I started out with a solid here. We know that this is an endothermic reaction, so what did I do? I probably added heat or fire to this to decompose it into this. Okay? Alright, so the next question is using the same equation, and it's going to ask us this. What mass of potassium chlorate must decompose to form 78.4 liters of oxygen gas at STP? So again, we knew that the fact that we had a gas here, they might ask us for volume. Okay? And the fact that we have STP is a hint that we're going to use a conversion factor for ideal gases of 22.4 liters per mole. So again, I'm going to leave my moles out of this here, okay, and we're going to go down here to start working backwards. So what I have here is I have a volume of oxygen, right, and I want to go to moles of oxygen because I want to line my moles up here once again, okay? So once again, I'm going from liters of oxygen, okay, and I want to go into moles of oxygen, right? So again, the whole point of getting moles is that we can control everything. So I want to line up my moles here, and again, this is the theoretical yield. Theoretical, what should happen? Okay, we're going to talk about percent yield later. Percent yield is what actually happened divided by what happened here, or the theoretical. So I'm going from liters of O2 to moles of O2. That's what I want to do right here. So I have down here 78.4 liters of O2. So again, I want to have my unit and my molecule written like this together. Okay, always they have to be in pairs. Okay, and a lot of times in different types of science like physics, we just have units, but in chemistry we have the units and then the molecule. They go together. You have to write both to understand what we're talking about here, okay? So 78.4 liters of O2, okay? So the fact that we have STP right here, I can go ahead and tell you that I'm going to have 22.4 liters of O2 per 1 mole of O2, okay? So once again, I have my units, my molecule, my units, my molecule, my units, my molecule. They occur in pairs. You have to write them all out like this. It's not going to work if you leave out the units like this. It's not going to work. Teacher's not going to be able to follow what you're doing, okay? So I cancel out the units, the molecule, the units, the molecule. I'm left here with moles of oxygen. That's what I wanted to see, right? Okay, so I'm going to go ahead and perform this calculation. And when I perform that calculation, we're going to take 78.4 divided by 22.4, okay? And that's going to give us 3.5 moles of O2. 3.5 moles of O2, of oxygen right here, okay? So now we can control the actual experiment right now. Okay, so here's my 3.5 moles of O2. So let me put this in red here just to show you that that's what we ended up with. So again, the whole point of this is to turn everything back into moles. So I'm going to put my 3.5 moles right here of O2. Now again, these are the moles, these are the ratios, the coefficients, right? They're different things, right? This is the actual moles. So if I want to start doing my conversions, okay, I'm going to cross multiply and I'm going to divide. Okay, so I'm going to say 3.5 times 2 divided by 3. Okay, so that's going to give me 2.33 moles here. Okay, now I'm controlling the situation once again with the number of moles right here, right? So this number of moles controls everything that I do. Okay, so this is the number of moles, so I can kind of control my reaction right here. Now they're asking me what though? They're asking me what mass. Okay, so let's just think about what we did. We talked about turning the volume into moles, right? And that's what I ended up doing here, right? And then I got all of my moles here, and now they actually want the mass of KClO3. So now that I have the moles, that's very easy, right? So I can basically take this number and come back down here, and I can find the mass of that very easily. Okay. So again, the point of what we're doing here is we're going first into moles. We control everything. Now I can do the mass. I could find the mass. I could find the volume. I could find the heat formation. But you got to know the number of moles first here. All the other information is irrelevant. I mean, if I have grams and liters, I really can't do anything with that until it goes back into moles here, okay? So if I want to find the mass of that, what I'm doing now is I'm basically telling you that I want to go from moles into mass, right? So let's just draw an arrow here. So now I want to go from moles of KClO3, and now I want to go into grams of KClO3. Okay, I'm just writing out the units here so you can see it. And that's the whole point of this. So now that I know I have so I have 2.33 moles of KClO3. And I want to go into grams. So we saw before the molecular mass of that was 122.55. So I'm just going to go ahead and rewrite it out again here. So we have 1 mole of KClO3 is 122.55 grams, okay, of KClO3. I'm going to write this out even though you think it's redundant. It's not. You have to write everything out. Again, units, molecule, units, molecule. These are going to cancel out. Okay, see it canceling out right there, canceling out right there. What am I left with? Grams of KClO. Okay, so when I go ahead and write this out, you're going to see that I'm going to end up with the same units right here, okay? So let's go ahead and multiply that out right now. So let's clear this out. So I'm going to say 2.33 times 122.55. And that's going to give me 285. I don't know why this keeps disappearing. 285.54, 285.54 grams of KClO3. Okay, and that's going to be the answer, the final answer to the question, okay? So we're still using dimensional analysis, right? But instead of writing it out in like 4 and 5 and 6, 7 steps, we're just doing it in little pieces because the goal is to have this central focus here of the number of moles that are reacting. That's the whole point of this type of a problem. You need to understand the number of moles. Moles controls everything. Everything passes through moles. So we pass into the moles, and then we might pass out. And usually, by the time we have moles, it's usually just 1 or 2 steps to get what we want. That's the mass of potassium chlorate that must decompose. It's to form 74.8 liters of oxygen gas at STP. Okay, so you see this common theme here that we're doing. I hope you can see this common theme over and over. We're just going back to moles. So I'm just doing mole ratios in this first one. Very simple. The next one, I was given a mass, so I found the moles, and then the mass, went into the moles here. Once I found those moles, I just did mole ratios, right? Pretty easy. This one, we had to pass into moles and then pass out to mass. But that's pretty simple stuff, right? There's nothing really too fancy about it. And I think by breaking it up like this to doing, just a little bit of dimensional analysis to get the moles, then organizing our data in a clear, simplistic fashion, it's much easier to see where we're going from here, because I could get the mass of this, I could get the mass of this, I could get the mass of oxygen, I could get the volume of oxygen, I could get the heat of formation. It's all one step away from this. So once you have moles, you're one step away. Alright, so the next question says, what mass of potassium chloride is produced along with 1.51 times 10 to the 24 molecules of oxygen gas? Okay, so now this is asking for slightly different pieces of information, but we can solve it the same exact way. We're just going to end up with moles, and then from moles we go back. Okay, so they're asking for the mass of KCl, but they're giving us molecules of oxygen gas. Okay, so what's going to happen here is I'm going to have molecules, okay, of O2, right? And I want to just go to moles of O2, right? Okay, so that's what I'm going to do first. Same exact method as before, right? Molecules, I'm just going to moles. Moles, we're going to go back up here, line up our moles, okay? Very straightforward, same process, okay? So I'm going to have 1.51 times 10 to the 24 molecules of O2, like this, okay? And I'm going to use Avogadro's number. Okay, so Avogadro's number is simply a number to group items. Like we would say like a dozen is 12, and Avogadro's number is 6.02 times 10 to the 23rd. That's a lot of eggs, right? If we ordered a mole of eggs, that would be a lot of eggs, right? The reason that number is so large is because that's the number of molecules or atoms that would need to be significant to be able to weigh them in grams, right? Okay, so we're going to have 6.02 times 10 to the 23rd molecules, I ran out of space here, but molecules of O2, right, in 1 mole of O2. Okay, and again, units, molecule, units, molecule, units, molecule. You got to write both, guys. You can't just leave stuff out. Finish the problem. So molecules of O2 cancel out with molecules of O2. What am I left with? My units, moles of O2. Okay, so why do I want moles of O2? Because I'm going to line up my moles again up here, right? That's the whole point. So if I went ahead and finished this out, I'm going to get a number here when I take 1.51 times 10 to the 24 divided by 6.02 times 10 to the 23rd. Alright, so when I go ahead and do this, when I take 1.51 times 10 to the 24 divided by 6.02 times 10 to the 23rd, I'm going to end up with roughly 2.5. It's going to be like 2.51 moles of O2. Okay, so again, write it out, guys. Write it out. Okay, you have the number here, you have the unit and the molecule. Okay, number, unit, molecule. Number, unit, molecule. Okay, so there's my answer. Okay, so why do I care about moles of O2? Because once again, we're going to line all of these up here. Let's just say 2.51, whatever. Okay, so 2.5 or 2.51, about the same. I'm going to cross multiply times 2 divided by 3. So I'm going to take 2.51 times 2 divided by 3. So I'm just going to get, right here, I'm going to get 1.67 here. And again, if I multiply 2.51 times 2 divided by 3, again, I'm just going to get 1.67 right here. So once again now I'm in complete control of the problem because I have all the moles here. Okay, so once again I went into the problem here with the moles, okay, and now I'm going to come out of the problem to find the mass of KCl. right here, right? So I want to find the mass of KCl. So again, I'm going to take the moles of KCl and I'm going to come back out of this down here. So I'm going to take the moles of KCl to start the next part of this problem. But if you line all these up again, you'll see that it's very clear to see what's going on. Okay. So what am I going to do here? Well, I'm going moles of KCl, and I just want to end up with grams of KCl. Okay, that's all that I'm trying to do right now. So that first little step is important because it tells us where we're starting, where we're finishing, and this is good form. If you want to do well in these problems, a lot of this is about good form, understanding what's going on. And the way that we're lining these up with the moles is really important because down the road, when we start getting into limiting reagent and excess, okay, so we have an initial, this will be what changed, and we have an excess down here. It's going to help you very clearly to see this in a to organize your data in a tabular fashion. Then down the road, when you get into equilibrium problems, you will already know how to do initial change, and in that case, it's called equilibrium. But what we're doing right now is not equilibrium. It's just dealing with, if we have a limiting reagent, we might have an excess here. This problem has no limiting reagent. I'm just telling you that this is important to understand how to write your information out clearly like this. Okay. So I'm going from moles of KCl. So how many moles of KCl do we have? Okay, I have 1.67 moles of KCl, like this. Okay. And how am I going to get the grams of KCl? Well, we're just going to take the molecular mass of KCl right here to multiply it. So 1 mole of KCl is 74.55 grams, like this. Okay, so here we go. Let's take our units here. I have the units and the molecule cancel with the units and the molecule, and I'm left with 74.55 grams per 1 mole, and I should have written KCl here. I'm going to get 124.49 something in there. So it's going to be about 124.5 something in there. Okay, grams of KCl, okay, and that's what I was looking for, right? There are my units. My final units were grams of KCl, and I knew where I was going before because I wrote this out because we want to have good form here, right? I'm going from moles to mass here, and then I ended up with the mass, and that's what I did. So again, we're seeing a common theme here over and over and over, right? We're always going to the moles, and then we're coming back from the moles if we need it, right? So over and over and over, same exact theme. Just different ways to ask information about the same problem here, okay? So let's go to our last question now. Alright, so now we have the final question of this reaction. It's going to deal with the heat of formation here. So again, let's review what we talked about. We knew we had a solid here with potassium chlorate here. It's going to decompose into another solid here, which is potassium chloride plus some gas here. And the reason that happens is that this is an endothermic reaction, which means I have to put heat into this thing to make it go. It's not going to give off heat. I have to put in heat to the reaction for that to occur. So maybe I put in some type of a flame or a fire, and I kind of burned it, and I ended up with this. Okay, so you could have just heated it up and melted it, but we had to put energy into it in some way. Okay, that's the whole point. It's going to absorb heat. It's not going to give off. So again, we're going to go through the same process we've gone through in all of these. I have moles here. And I'm starting out with 3.92 liters of oxygen in STP. Well, I need to find the number of moles of oxygen, right? So again, we're going to start out down here, 3.92 liters of oxygen, and I want to go to moles of oxygen, right? Okay, so that's where we're going, right? So liters of oxygen into moles of oxygen. So I'm going to start out with 3.92 liters of O2, and I know that I'm at STP, right? So what does that mean? Well, again, I know that I have 22.4 liters per mole of an ideal gas, if it's ideal, which it is. We're assuming the gas is very small. There's no interstatic reactions between the charges, and the collisions are perfectly elastic. That's kind of getting into the definition of ideal. But if it says STP and the gases are small, we assume they're ideal. Okay, so we can use this conversion. That's all that means. I wanted to end up with moles of O2, right? So I started out with 3.92 liters of O2. Okay, there's 22.4 liters of oxygen and 1 mole of oxygen, right? Okay, so what do we get when we divide that out? Well, we know that the units are going to go. So I have the units and the molecule gone, right? Liters of O2 are gone. And now I have the units and the molecule here, right? That's what I wanted to end up with, so I'm in the right place. You have to write all of this out. You cannot skip these steps. You cannot skip these steps. So it's going to be 3.92 divided by 22.4, and that's going to give me a number of 0.175 moles of O2. Okay, and that's the number of moles of oxygen. So then once again, what are we doing here? Well, I'm trying to get my moles back up into here to start controlling this reaction. Okay, so I'm going to take this, I'm going to put this up here. I guess I'll draw it with a red arrow up to here. Okay, so I'm going to end up with 0.175 here, and these are my actual moles. And then I just go back into what I was doing before, right? To get my mole ratios, I 0.175 times 2 divided by 3. So 0.175 times 2 divided by 3, right? And again, that's going to give us something smaller, right? That's going to give me 0.11, let's just say 7. I'll stay with 7, okay? And since this is a 2 also here, we cross multiply and divide, so it's going to be 0.117 like this. Okay, so here we go. I'm controlling the equation now with the moles, right? I have the moles. I know what's going on. There's no limiting reagent here, so I don't have to deal with an initial condition and choosing and subtracting to get the excess. This reaction is going to go fully. This is a simple problem. Okay. Now, the question asked me about the heat of formation, right? Well, the heat of formation, for how much heat is required, right? Okay, so I got to put heat into this thing, right? So I'm going to use green to show the heat here. And you can use basically any of these that you want. I found the moles of all of these, but in this particular problem, you didn't really need to. But I just went ahead and did it just to illustrate that we should just pretty much do this all the time so we can have all the information. So in that case, I can just use whatever I want. So I'm going to go ahead and just use the oxygen in this case. So I'm going to take the moles of oxygen here like this. I'm going to take it back out. So I want to go from moles of oxygen, and I want to go into kilojoules. So once again, I had to go into here before I can come back out, right? So that's the whole point of this, okay? So I ended up with 0.175 moles of oxygen, like this, right? And now we're going to get into the unique ratios here of this heat of formation. This delta H here, what does that mean? How do I put that into a dimensional analysis problem here? Basically what we do is we know that this heat of formation is good for all of these ratios. Okay, so for every 3 moles of O2, I get this much heat. For every 2 moles of KCl, I get this much heat. And for every 2 moles of KClO3, I get this much heat. And it doesn't matter which one you choose. I just chose oxygen this time, so fine. I chose oxygen. It doesn't matter. I could have chosen KCl. I'll get the same exact thing because these ratios will adjust. Okay, they'll adjust very quickly. Let's go ahead and calculate that now. I know that for every 3 moles of O2, so 3 moles of O2, I'm going to get 89.4 kilojoules. So I'm going to get 89.4 kilojoules released. Okay, and so that's how the conversion works. It's whatever you chose, right? I chose oxygen, so I have this much heat is released for every 3 moles of that, right? So that's not a problem. So again, units, molecule, cancel, units, molecule, cancel, and again I'm left here with the units release. In this case, it's just the total heat of formation, so I'm not going to have a molecule anymore, but those are the units that I wanted right here, kilojoules, right? Okay, so we're going to take 89.4 times 0.175 divided by 3. That's going to give me 5.215 kilojoules of heat released from that reaction when 3.92 liters of oxygen are formed. And again, was this even relevant? No, I wanted to know about moles in the end, right? That was the most important thing. Now, I'm just going to prove something to you. I'm going to prove to you that it doesn't matter what I used. In this case, I used oxygen, right? Okay, 0.175. But what if I wanted to use potassium chloride, right? What if I wanted to use it? Let's see if it works, okay? I mean, if what I'm telling you is true, it should work, right? It is true, so it is going to work. So for the potassium chloride, I'm going to use blue so you can see down here. And I had a different number of moles there, right? Okay, so for the potassium chloride, right, My goal is to now go from moles, stay in blue, moles of potassium chloride into just kilojoules again. Okay, release. I'm going to start here, and I'm going to stay, well, I know that I have 0.117 moles of KCl. Okay, I'm going to deal with the ratio now of the heat of formation. It's a little bit different. So now I'm going to say for every 2 moles of KCl, I get this much heat. So for every 2 moles of KCl, right, I'm going to end up with 89.4 kilojoules here. And I'm using just it doesn't, and again, it doesn't matter which molecule I'm using. This time I'm using KCl. If I did it right, I should get the same exact number that I got for oxygen because it doesn't matter what I use. Okay, so let's cancel out the units and the molecule, I'm left just with kilojoules. So 0.117 times 89.4 divided by 2, and that gives me the exact, pretty much the exact same thing. I got it off by a little bit, but it's like 5. In this case 5.22 or something. So it's the same thing. It's just off by, you know, a few units because of the rounding errors in there. But it's the same thing. So when you're doing the heat of formation, it doesn't matter which one you choose. You just have to use the correct ratio. So once again, let's just review what we did here, okay? I basically wanted to know how much heat is required for this much oxygen to be given off, right? So I started with the oxygen. I found the moles of the oxygen here, okay? I put it back in. I found all of my moles, okay? And then from there, whatever they ask us, we can find basically in one step. The trick to this one is that the ratio of the heat, you have to do it to these coefficients. So I knew in the green one here that I had 0.175 moles of O2, and then the ratio was for every 3 moles of oxygen, this much heat is released. Okay, cross it out, there's my answer. And then I said, well, it doesn't matter which one I use, right? I could have used KCl, right? So I knew I had 0.117 moles of KCl, and I just wanted to show you that it's the same, but now the ratio is different. It's 2 for every 2 moles of this, you get this. So I said, okay, 0.117 moles of KCl. For every 2 moles of this, I get 89.4, and I got the exact same answer. So again, it doesn't matter what you do. The common themes here that I'm trying to point out is that when we're doing these types of problems, it's very useful to organize your data in a clear fashion just to show the number of moles here. It's simple, it's organized, and then you kind of have a focal point of where you're going. At least if you have the number of moles, you have like a central station where you can move in and out of, right? And so that's the whole point. Once these problems get more complicated down the road with limiting reagent, or when we get into equilibrium, when we get into these mystery products and reactants, these tables are going to become even more useful. So I strongly recommend that you start to learn the information this way, because as you get further into chemistry, it's going to help you out a lot in terms of making these problems much more simplistic and bite-sized for you to learn. All right, that's all I got for this video. Thanks for watching, and I'll talk to you soon.